And now let's focus on 3D and visual sensors. So why do we need a perfect sensor? A drone can do a lot with an inertial motion unit, IMU, a compass, a GPS, but to be autonomous and perform useful tasks, you may also need to measure the distance with a known surface. For example, a sonar to measure the distance with the ground, so that's height. Detect objects, but you don't want to map them, you just want to detect them to avoid collisions. You can potentially want to scan and map the environment in 3D, for example, a laser or rotating laser to map the ground or the space around you. And you may need to reposition the drone inside a known volume or compared to your surface, compared to the ground. So each sensor has a specific goal, and usually drones would carry multiple sensors that would solve a specific problem. But unfortunately, there is no perfect sensor that could do everything automatically. Sensors are here to solve different problems. For example, do you want to avoid collisions, knowing that by default you will have nothing in front of the drone, so the collision avoidance is used rarely? Or do you have a payload scanning the environment for remote analysis, for example, scanning a mine in 3D from the sky? Or perhaps you need an autonomous flight around objects under human supervision. So it means that by default you will have something in front of the drone and you have to follow this object. Or perhaps you even need full 3D awareness for autonomous flight in an unknown environment, for example, deploying a drone inside an apartment without knowing the map of the apartment. It's important to characterize the speed and range of your sensor. Do you need assistance for takeoff and landing or for cruising? Depending on what you need, sensor will be very different. Also, what is the risk you can afford to take and what is the efficiency you are trying to reach? Do you need a perfect sensor or do you need a good enough solution? Do you need full mapping or simple repositioning in a known map? So to summarize, there is a lot of different needs and a lot of different sensors, and there is not a single 3D solution for all needs. There is no perfect 3D sensor. So if there is no perfect sensor, what do we do? First, you select the right mix of sensor for your specific case. Then reuse sensors and libraries from other sectors where they spent a lot of time developing them, for example, the automobile industry and robotics and augmented reality. For each sensor, know their blind spots. There's always a blind spot for a sensor, but you can also play to their strength. And at the end, the only good answer is to have different sensors, each with their blind spots, to mix them together and to fusion the data coming from all your sensors. It's called sensor fusion. If you look at the illustration on the right, it's coming from a car. A car can have a laser-based sensor called LiDAR. It can have a sonar. It can have ultrasonic. It has a lot of camera. To summarize, it has a lot of different sensors. On all of them have blind spots, but together with a good sensor fusion, they provide a good system to drive the car. So what if you need to position your drone in space? And let's focus on outdoors first. Of course, you have GPS, but it's not very precise, up to 3-meter precision. So today, you have the choice to integrate a new technology called differential GPS, or RTK. It's been around for quite some time, but the good news is that in the last years, you had a price drop, quite impressive price drop. So now it's in the range of $200–300 for each chip. You need to integrate this chip very precisely and finely with a high-quality GPS antenna. So it's a precision work. Then you put a base in a 20-kilometer radius around your drone that will act as a normalization station, and you need a link between your drone and this station. So it can be radio or IP, it can go over Wi-Fi or the mobile network, but at the end of the day, you need a link. As a result, the base station will analyze the conditions, will normalize the GPS signal, and will send the information to your drones in a 20-kilometer radius. And your drone will be able to normalize the signal, and you will have a 2-3 centimeter precision instead of 2-3 meters. So that's quite an impressive result for a reasonable price. So GPS is great outdoors, but what if you need to go indoor? We can work with ultra-wideband. So it's a time-of-flight system. It is not like beacons, Bluetooth beacons, where it's a signal strength system. That would not be very precise. With time-of-flight system, you get a very precise localization, even in very large buildings. You can have a 10 centimeter precision, even in a warehouse. So there's two ways to deploy the ultra-wideband. You can have a very simple and dumb tag, and the smart connected anchor that you would deploy all over your building would locate this tag. The other type of ultra-wideband architecture is to have a smart receiver and simpler anchors, and the receiver itself will do the triangulation of all the anchors and will know where it is. So that's the one we want for large drones, because we can afford to carry a microcontroller and we can afford to give power to it. It is not important compared to the other source of power consumption on the drone. So that's the one you want for your smart drone. So what if you want indoor localization, but you can't afford to deploy anchors all over your building? Perhaps because it's a house, or perhaps it's a non-building, you're going there for the first time. So what you can do is use a mix of sensors, for example 3D sensors like Intel RealSense, plus a camera and inertial motion units that you have on the drone already. And with a very complex piece of software called a SLAM library, you will be able to perform simultaneous localization and mapping of the area around you. So it means that the drone, as it flies, will build a map of everything that is in front of the drone and will be able to know where it is in this 3D space. So it is great, but it is an advanced technology, and try to work with ultra-wideband or GPS if you can afford it. Note that Intel released a wonderful free SLAM library that is working with the ZR300 RealSense camera and is doing data fusion between RGB, color information, depth information coming from RealSense, and inertial motion units. So it's a very advanced SLAM library that is available for you to integrate in your drone project. Sometimes you need visual piloting, indoor or outdoor, but you don't need the full SLAM complexity and details. So you can use tags or 3D objects to act as visual anchors for the drone to recognize and to perform tasks. For example, you could have marking on the ground to pilot the drone on an airport. You can do that with libraries like Visp or IR Toolkits. It's a set of robust, highly optimized codes that were developed for augmented reality in the past and are now reused for robotics and drones. So you can have 3D positioning of your drone in space just by looking at a tag on a wall or on the ground. And you can have advanced features, for example, understanding where a 3D object is in space compared to the drone, or where the drone is in space compared to a 3D object. It is very interesting, and we'll see a lot of that in the following years. Now that we understood the different usage model, let's focus on sensors. So if you want to measure a distance, for example with the ground, to have the height, you can use a sonar or a one-dimension laser that will do that. So it's required if you want your drone to hover at a very precise height, because if you don't have this kind of sensor, all you have left is a GPS, and GPS is not very precise. For example, if you want to perform a smooth landing, this kind of earth measurement is interesting. So here, pictured on right, we have a very simple sonar and a LiDAR, a laser-based edge measurement that is very precise. The first type of 3D sensor you can have on a drone is a binocular sensor. By using two cameras and performing a very complex computation, you can recreate a 3D image. So you have two options for this heavy computation. Either you can run a very intensive software on your CPU or GPU, but it takes space to host the computing device, and there's weight, and it's expensive, and it's generating a lot of heat. Or you can use a dedicated chip bundled with the two cameras, and it's compact, it's a lot cheaper, it's very light. As an example of this kind of binocular bundle is Intel RealSense technology with infrared grid illumination technology. As a result, you get a 3D depth map on RGB image coming directly from the sensor to your drone, so you can code whatever you want with it, like collision avoidance or scanning an object. For the current generation of Intel R200 RealSense camera, we have between 4 and 5 meters of depth information, so it's good for low altitude, low speed collision avoidance, as an example. And you get information about what is in front of the camera. So imagine it's a webcam, let's say 120 degrees by 60 degrees vertically, and you can bundle different sensors to have 360 vision around the drone. Another way to get 3D information is by reconstructing a 3D space from a 2D sensor. As you know, lasers are very good to measure distances, and if you mount a laser on a rotating base, you can get one dimension of depth information 360. So that's called a LiDAR, and by rotating this one dimension LiDAR vertically, you can get a little more than just one dimension. For example, you can get 360 degrees by 15 degrees. So it's not really full awareness of everything that is all over your drone, but it's still interesting if you want basically one dimension of information. For example, if you embed this kind of sensor vertically under your drone, you can scan the ground when the drone is advancing. Pictures on the right, you have a very typical model of a LiDAR called Velodyne puck, and on top of the photo you have the output of this kind of sensor. Now, if you are interested in collision avoidance and you want long distance while your drone is moving at high speed, for example, but you don't want the full weight and price of a LiDAR, what you can do is take one camera and compare the succession of shots taken while the drone is moving in one direction. To do that, you can use a dedicated chip from Movidius as an example, and that's how collision avoidance is done on a DJI Spark drone, for example. You can see videos of that on their website. So far, we've seen a lot of sensors used to help you fly autonomously and avoid collisions. And with the LiDAR, we've seen that we could scan the ground. But what if you want to embed a software payload on your drone and be able to reconstruct an object on the ground in 3D by flying around it? So it doesn't really help to fly autonomously, but it may be useful if you want to scan a 3D object. So you have some software stacks that are very popular to perform this kind of task. For example, Pix4D, FPV camera, drone deploy, etc. Sometimes you want to dedicate a specific piece of hardware to a specific part of the flight. For example, there's something called optical flow. It means one camera is facing downward, recognizing the pattern on the ground and making the drone hover without drifting. It's typically linked to the flight controller itself because it is only used to control the flight. You don't really need that in your software payloads. Or you can, for example, have a barcode reader or a RFID reader embedded as a payload for your drone. So not everything has to be done in software. Sometimes it makes sense to have dedicated hardware to perform certain tasks. As an example, here you have an illustration of Pix4Flow, a typical plugin for flight controllers. So we've seen a very simple computer vision task like recognizing pattern on the ground. But what if you want to go further and recognize objects, know where they are in space, reconstruct objects in 3D? All these kind of tasks need a lot of CPU, a lot of memory, potentially data files. So this kind of library is better done on the processor, on the compute board, for example Intel Aero compute board, and with one camera you can do a lot of things. We recommend you check AR Toolkit and Visp. They are wonderful free libraries that can perform very advanced computer vision tasks from a drone, and it's integrated with ROS for Visp. So to summarize, there is no perfect sensor that will be able to see everything and solve all your problems. Each sensor has very specific features and is solving a very specific problem. So be clear about your goals regarding your fly stack and your user payload. Try to differentiate what is for the fly stack and what is for the user payload. At the end of the day, your drone will probably have several sensors and you have to merge data from different sensors to have one composite information.